what they asked me to talk about was string theory, symmetries, and anomalies. And this can be sort of understood in two ways, and I think both are interesting, so I'll be talking about both. One of them is the thing I will discuss today, which is string theory anomalous? I believe the answer is no, otherwise we wouldn't be working on string theory. And precisely what I mean by this is that the gauge symmetries of string theory don't have anomalies. So diffeomorphisms and gauge symmetries in different versions of string theory don't have anomalies. So the first thing I will discuss during today and perhaps tomorrow is anomalies in string theory. And we will see, at least at the level that we will check, which is a bit superficial, that there are no anomalies in string theory, and then you can go forward with some of the methods I will describe and check further and further, and so far nobody has found any anomaly in string theory, which is good news. We believe this is a good theory for gravity, so you shouldn't have anomalies in the sense of gauge anomalies. You could also try to understand if there are symmetries in string theory. I will really not say anything about this, but there's a whole field of research here known as the swampland that tries to argue or tries to start from the point that there are no symmetries in string theory or in any theory of quantum gravity. As I said, I will not discuss this, but we believe there are no symmetries in string theory. Everything that could be a symmetry, global symmetry, is gauged. So this will be the first part of my talk and my lectures. And then I will move on to discussing how to obtain symmetries of quantum field theories in various dimensions. I will tend to work in higher dimensions than most of the lectures so far. So for me, QFTs tend to live in 4, 5, 6, 7 dimensions. How do you obtain the symmetries of such QFTs from string theory? So I will explain first of all how these two statements are compatible. How on earth can I start talking about symmetries, global symmetries in this case, of a field theory using a construction that does not have symmetries? And then I will explain how in recent years we have understood from many points of view, condensed matter were the first, and then high energy and mathematics, that the structure of symmetries in quantum field theory is very nicely encoded in a theory that lives in one dimension higher known as the SymTFT. So I will describe some of that in coming lectures. But the first part for today and perhaps tomorrow will be to try to understand what happens to the apparent symmetries of string theory, gauge symmetries, and I will try to show that they are anomaly free. So this is a consistent theory. This is of course a very old topic, and basically nothing I will say today is even remotely new. Most of it happened before most of us were born or were little babies. So there's by now lots of reviews that you might read that fill in some of the details that today I won't be able to discuss in any detail. The thing I will do is try to reformulate some of these classical results in a language which is a little bit more modern and which was already covered to some extent in Max's talks last week. So I want to think of the anomalies of string theory in terms of the anomaly theory. So for me, anomalies arise because I have to define the phase of the partition function, coupled to some background. So let's say that you have some d-dimensional manifold and some background B, and this could be a background for a global symmetry. Could also be the metric. So I will dump all of these into B, what I call B. So I will study at the same time diffeomorphisms and changes in internal symmetries in SU2 and so on. And the standard example for anomalies is something you have seen already in this school. Is the case of a Weyl fermion. You try to define its path integral in an arbitrary background, and you encounter that you cannot define the phase properly. properly meaning that you cannot define it unambiguously. The thing you can define unambiguously is the partition function modulus squared, or perhaps if you prefer the modulus of the partition function. So this thing you can define, but the phase is typically ambiguous. And it's some phase that depends on your manifold and the fields.
Will you choose the background fields always to be real?
To be real, here I will choose them real, yes. Yeah. So the way I like to think about this, when you write things in this way, I'll think of the space of all backgrounds for, sorry, this program. The space of all backgrounds that you can put, modulo gauge transformations. And what we want to understand is if you start at some point here, you define some partition function for the Weyl fermion as a function of your manifold and the point in which you are in this manifold. What happens to the phase of this partition function as you take loops, as you travel in this configuration space? So this is a picture that's best suited for continuous symmetries. So that's the thing I'll have in mind when I draw this picture, although the results I will formulate later are general. In this case, this is best for continuous symmetries. And the physical question is what happens to the phase of the partition function, this thing that's ambiguous, as I travel in the space of configurations and I come back to the same background modulo gauge transformation, so the same point in this quotient space.
Do you have a notion of parallel transport?
Yeah, there's a notion of parallel transport. Yeah. I will sort of give you an implicit definition of what this is in the lectures. So there's two cases, two ways the phase can change. Okay. So here I'm thinking of something which is not quite a function. It can change as I move in my manifold, I come to the same point. It's going to be a line bundle. So this is going to be a section of the determinant line bundle, it's called. The nomenclature is something that you should already understand from the lectures last week. If you try to construct the path integral for a fermion, you are effectively constructing a Pfaffian or a determinant that depends on the background fields. So the name determinant is because of that. The fact that it's a line bundle is because as I move on this manifold and I come back to the same point, I can pick up a phase. Now, two things can happen in line bundle that can make you pick up a phase as you parallel transport. They can be local curvature. That is, you can take a little loop here, infinitesimal loop, and the phase can change. That tells you that your space is curved. In this case, we talk, if you have curvature in this bundle, we talk about the perturbative or local anomaly. Just to be clear, the local here refers to local in this picture. There's also a notion of an anomaly being local in space-time, meaning it happens in the sphere and doesn't require more complicated manifolds. But here I just mean local in this space. And you can have flat bundles. So there's no curvature. But they can have Hall norms, non-trivial Hall norms. So imagine that I do something like this. I go this way, and I come back to the same point. I'll try to draw it that makes sense. Something like this, right? So I could have a flat bundle, but when I go around some cycle like that, I pick up a holonomy. In this case, we have what's called the non-perturbative or global anomaly. Okay. So I'll give examples of both during the lecture. Now, there's two ways I could do this, or more than two, in fact. Originally, the ones that were discovered were these local curvature anomalies by computing triangle diagrams, and people realized that they couldn't define things properly, they couldn't regulate the integrals properly in a way that preserved covariance and gauge transformations, for example. And eventually, this ended up being connected to the things I'll describe. Alternatively, you could try to define a connection in this determinant line bundle. I'm going to use a different approach, which is due to Dai-Freed. It's, of course, motivated by these considerations and completely equivalent. So what Dai-Freed told us is a way of defining that phase in there for the partition function. You might be also interested, if you read about these things, to read about the beautiful physical interpretation given by Witter and Yonekura. And what is this? This is a prescription for constructing the phase of that object. They tell us, and I will explain why this makes sense, that whenever you're in this kind of situation and you want to construct a partition function of a fermion in some background, the modulus you can always define in your favorite way. So, for example, you could add an opposite fermion with opposite fermion numbers. This thing can be gapped, so that thing has no anomaly, and then you take the modulus of that thing. So the square root of the modulus of that thing. The interesting bit is the following one. Dai-Freed told us that you can define this object by computing the eta invariant on a manifold that I'm going to call N with bundle B bar. Okay, I need to define what those objects are. So N is a D plus 1 dimensional manifold such that its boundary is empty. So pick one. We'll be concerned in a second how much the choice here matters, but for a moment just pick your favorite one. Yeah.
Quick question. So those kind of anomalies that you sketched there, they're the ones that can be detected on a mapping torus in one finite dimension, right? Mm-hmm. There are ones which cannot be detected.
Yeah. I'll come back to that point later. Yeah. Okay. Any other questions? Okay. So that's N. B bar is an extension of B to M. So the picture is I have my manifold M here. I pick some extension here, I call that N. I have my fields B here, and I pick some extension. Again, there are choices here. Pick one, and you go to some configuration of the B fields in N. Now, as I mentioned before, B is whatever structure I want to put on my manifold. It could, for example, include the spin structure. So that might restrict my choices of N. I need to be able to extend my structures to that manifold. Yeah.
There is no such extension.
Yeah, very good. That can happen. And that's the statement that basically a field theory has choices of phases. This is the statement that field theory can be coupled to SPTs. So whenever you cannot extend this thing, technically you're in a non-trivial Bordism class. And you can choose to add phases to your partition function by putting a SPT that detects a Bordism class.
What if it is in the class C and you do not have a finite, it's not in the portion class?
Sorry?
What if it's not in the portion class of the Bordism group, such that you cannot just stack finite?
Well, I mean, every manifold is either trivial or non-trivial in Bordism. If it's trivial, I can do this. If it's non-trivial, I can pick a reference generator that I like and dress it with a trivial manifold. Right? So this prescription is for trivial manifolds. Now, in each Bordism class, you get a choice, which is to that Bordism class which phase you assign to it. So you need something that map goes from Bordism class to phases, and those are SPTs. Yeah. Any other questions? All right. So these are these two things. Then d slash here is just the Dirac operator. On n coupled to B. So there's a fermion in one dimension higher that couples to B in the same way that you write fermion coupled to this. So if this was fundamental, this would be fundamental, and so on. Basically extend it. If you want to make this a little bit more physical, the paper by Witten and Jern makes this very beautifully with the natural constructions of a fermion. Very good. And then the eta invariant. And if there are any mathematicians in the audience, I apologize. This is not, was often called eta in the mathematical literature, but I think that's going to be convenient for me. It's very close, of course. So eta of the Dirac operator. In my definition, that's 1/2 of the dimension of the kernel of d slash plus the sum for non-zero eigenvalues of the sign of lambda. So very often in the math literature, this thing is called eta. I'm going to call the whole thing eta, just to make this formality prettier. Okay.
What is lambda?
Oh, sorry, yes. These are the non-zero eigenvalues of D and B bar. So take your Dirac operator, compute the spectrum, and you'll have some zeros and some non-zeros. For the non-zeros, if they are positive, you get +1. If they are negative, you get -1. I believe Max already introduced this formula last week. So the only thing I'm going to say is that there is a way of regulating this thing. This is +1 and -1 in infinite series, but it's not hard to regulate. One of the things that Atiyah, Patodi, and Singer did was, in fact, show us that this can be regulated in a way that makes sense. All right. So I think now I have explained all the ingredients in this formula.
Excuse me. So that's the suggest that e to the 2 by I eta is just a plus or minus sign. There's no other value. Because this eta seems only a half integer.
Yeah. Appearances can be this. So this sum over signs has to be regulated.
Okay.
And
the other value.
yeah, this ends up being some sort of zeta function if you want, and it can take fractional values easily. Yeah.
So, but they can be some rational number.
In all the examples I know, they are rational, yes. I think that's a theorem, but I'm not sure. Okay, very good. Any other question? All right. Yeah, sometimes you will see in the literature this formula written in a slightly different way. For example, in the paper with Witten and Jern, sometimes they will write something like 1/2 of the sum over all lambda over the sign of lambda, and to make this true, I'm going to assume that the sign of 0 is +1. It's not important. It makes the formality a bit more compact if you like that. Right. Maybe I'll go here. Right, so this is what Max was asking a moment ago, a loop in, how do I call that? All B mod G. In this picture, is associated with the mapping torus. Okay, so if you imagine transporting your space-time MD along that path, you will start with MD with your fields P. You will transport it. Here, for the moment, I'm keeping MD fixed and I'm changing B. I'm going to drop this assumption in a second. Here you get another copy of MD, but B might have been gauge transformed. So this is some gauge transform. Okay. Now, because they are gauge transforms, I could conceivably glue the two ends here. And this is why this is called a mapping torus. It's really a torus, or a generalization of a torus.
Sorry, maybe I missed this. What's all B?
Which one?
All B?
All B, sorry. It's up there. It's the space of all possible backgrounds that you can consider for your B.
So it's like a stack.
It's like yeah, I'm quotienting by the gauge transformation, so it's kind of a stack here.
You glue only BG is equal to B? When you say you glue,
Yeah.
you glue only BG is equal to B?
No, these are gauge transformations. So I'm allowing myself, so I'm imagining the Lagrangian is invariant in this transformation, so allow myself to glue. Actually, the fact that I'm gluing is not going to be super important for me, but I can. All right, so let's see what this prescription by Dai-Freed tells us about what happens under this process. So I start with my set. This is a modulus, which is fine. And then I have a phase, which is eta of my manifold n, some extension, just open up here. Is the good notation consistent? I think I'm calling this p/n p bar. Okay, so that's what Dai-Freed will give us for the partition function here. The way to picture this is I'm basically gluing manifold n here and computing the phase by computing the eta invariant in this manifold. Yeah.
So you are considering all the gauge transformation here with BG.
Or any possible transformation. Yeah.
So you don't distinguish between local and global ones.
No.
And that's why you have the kernel there, right?
That's why I have the what, sir?
You have the dimension of the kernel in the definition.
Yeah, that's going to be important for that, exactly. I'm going to do the example of Witten's SG2 anomaly. And in that case, for example, this part drops out. And this one is the one that matters.
So this is a universal.
This is a universal formula. It captures both local and global anomalies. Yeah. Yeah, I'm going to explain all that. That's going to be the next 40 minutes or so. Very good. Any other questions? Okay, very good. So now we can try to sort of, by adiabaticity, you can try to sort of see what happens to a partition function if you start adding little bits here of this torus. And you can easily convince yourself that the partition function, by this sort of parallel transport prescription, and the parallel transport is here where it's implicit, in this idea that I'm going to glue little by little, the partition function of MD after the gauge transformation, but by what I mean is the partition function here, after I go through this mapping torus, It's going to be the same phase, or if you like, the partition function after a gauge transformation, but the modulus doesn't change after a gauge transformation. And then e to the 2 pi I, eta of d on m plus t b bar. And I'm abusing notation slightly. I'm including now in this b bar the extension of b that lives inside the mapping torus. So basically, I'm gluing these 2 bits. I'm gluing this n and the mapping torus in here. Yep.
B bar G maybe? No? B bar G? Representation.
Well, this b bar, this is b extended to everywhere. So we have the condition that on this end is bg. On this end. So b bar lives here, lives on the bulk. And if you want, you can put the boundary condition here, it becomes bg.
So you have chosen the same extension?
Sorry?
You have chosen the same extension?
Yeah, I'm choosing the same extension, actually. The idea of parallel transport in this graphical language would be, I start with this choice of extension. That's where I start. I start adding little slices here to the same extension until I construct this whole torus, and that will give me the parallel transport.
But previously the V bar has only one boundary, right? So you're extending the formula to the case with 2 boundaries?
Well, after I glue, I still have one boundary.
You divide 2 as a single boundary in a sense.
No, the bark is one boundary.
Oh, yes, there's something I haven't told you, which I'm going to tell you next, yeah. So the data invariant, I haven't told you how it behaves under gluing. That's going to be my next step. Yeah, indeed. So in principle,
Confusion because you just drew B bar above the torus.
yeah,
It's not clear like whether the picture refers to the torus or to the whole thing.
right. So B bar for me will be whichever extension of B you pick up on the bulk. So you have a piece of the bulk here, which is n. A piece of the bulk here, which is the mapping torus. I'm going to call the extension to everything, to any extension I pick, B bar.
But at the end, you were not going to end up with the same extension you started from. You changed the boundary conditions from B to BG smoothly, adiabatically, but also B bar changes adiabatically. So the B bar at the end of the process is not going to be the same as the B bar at the beginning of the process.
Yeah, so think of the starting piece here. You remove all these mapping torus. You get a B bar in here. And I start adding little bits here without touching this B bar. Each time I add a little bit, I have to extend what I mean by B bar to define it here. So it's true that this B bar has a boundary here, which is B. And once I finish extending, we have a boundary condition, which is BG.
Yeah, so that the location of B bar is not the same B bar as the beginning, it's another B bar. That's why I said
Yeah.
Just put a prime on it.
Yeah, I'm going to put a prime. Yeah. Okay. Thank you. Okay. Yeah. Yeah, and I apologize. I might do this thing again. For me, B bar just means extension, right? Double repeat extension. But yeah, I'll try to be careful. All right. So what I want to do is to compare these two phases that I get here. And for that, I need a couple of properties of the data invariant. So let's say that you have a manifold M, and you compute the data invariant on M, some choice of extension, some background fields. Let me say M. This is the same as minus data invariant computed on minus M, meaning M with the opposite orientation. Okay, so if I change orientation, I get a minus N. Oh, so modulo 1. So if I change orientation, I change the sign here. second property. I will not prove this, but if you want to see the proofs, these are in the paper by Patodi and Singer, I think. And the second one is if z is x plus y. So I have a configuration like that one. I have some z, some x. So y, that can be complicated. I can join them to construct z. So I'm assuming here that they have the same boundary. Boundary of x is minus boundary of y is on manifold W. So then I have a set which is, after gluing, something like that. So say that you do a gluing like that. They cannot glue in that we are doing up there. Then again, the eta invariant behaves nicely. So eta invariant of the Dirac operator on x plus the eta invariant of the Dirac operator on y is the eta invariant of the Dirac operator on z modulo 1.
Is it not z equal to x times y?
I'm using, yeah, it's notation really. This means, yeah. So if you notice in the partition function, this appears exponentiated. So the phase of the partition function will multiply as you want.
But actually, it's not an abelian thing, right? Because y plus x cannot happen.
Yeah.
Well, for me, y plus x just means glue. So if they have the same boundary, there's a manifold you can define by gluing the boundary.
Part of the same part of the boundary.
Yeah, because y has more boundaries.
Yeah, more boundaries, yeah, exactly. You pick a boundary. So, okay. I'm getting the feeling I'm getting a hard time with notation, so I'm going to be careful from now on. So you glue along the common boundary, which I called W in this way. So pick a boundary, and that's what plus means for me. Yeah. Thank you. Please keep the questions coming. I'm just joking.
So the remaining boundary doesn't spoil anything.
No, exactly. You can have more boundaries, and that doesn't change.
Usually you have to sum over the states, right? So when you cut things together.
Yeah.
Whereas the eta invariant corresponds to one particular the boundary condition.
So if you want to think in that language, this is an example of an invertible field theory.
I see. So here the space is one dimension, so you can just cut it.
But I mean, as you wrote it, the formula eta plus eta equals eta doesn't make sense because eta of dx depends on the data on a boundary that doesn't exist on the right hand side, you see? It doesn't even depend on the same variables the way you wrote it.
Just cancels out. I mean, there is a dependence, but
Probably there is implicitly some boundary.
Yeah, there's a choice of boundary conditions, the APS boundary conditions here.
Yeah, you have to choose some boundary conditions and then show that it cancels.
Yeah, that's the way.
It's only with APS boundary condition.
Yeah, so, yeah.
Like for positive frequency.
Yeah, that's assumption, I think. All right, so I need these properties to to prove the following thing, which is how are those two partition functions related. So if I now try to construct set of MDBG, and I want to compare it with set of MDB, the original one, by those properties in there, I get that this is e to the 2 pi I eta Dirac operator on T with this choice P prime. Okay. right? So that's what it is. The anomaly in this formulation comes from an eta invariant evaluated in a torus with some choice of extension. This is a nice way of seeing this. So construct T tilde, which is T glued on the two ends. So so far I've been treating T as a cylinder, but I'm gluing the two ends now using the gauge transformation. And then I can ask myself, what's eta of B bar T tilde with this bundle on top? The fact that I'm gluing, because these are the gauge transformation, just means I have a non-trivial bundle for this B bar prime. And in this case, assuming now this is a manifold with a boundary, so I'm going to assume that T tilde is the boundary of some manifold S. So assume that such an S exists. The interesting case for global anomalies is when it doesn't, but for local anomalies typically it does, because you can contract this little loop to 0 smoothly. So you can sort of fill in this picture. This is the index of the Dirac operator on S with some extension, B prime prime, if you want, minus the integral on S of A roof of tangent of S times the Chern character of E. So I have to define these things. Okay, what's the index of a Dirac operator? And here I'm assuming even dimensions. So if you're in an even-dimensional spacetime, you can decompose any Dirac spinor into negative and positive chirality.
Sorry, S is even dimensional, T tilde is odd dimensional.
Yeah, so let's count dimensions. We started with some theory that I'm going to take to be even dimensional, because I had a wire fermion, and that only makes sense in even dimensions. Now this mapping torus is odd dimensional, and this thing is in one dimension higher, so it's going to be even dimensional. So the index is defined as, well, formally like this. And what this means is the number of positive chirality zero modes minus the number of negative chirality zero modes. Okay, so that's the index. I emphasize that this is an integer. At this point, there's no subtlety. There's some assumptions of the nature of the operator here, but those are satisfied by the Dirac operator. So this is indeed an integer. And the idea here is that if you have a couple of zero modes of opposite chirality, you can give them a mass, just write the mass term. The index will not change, but typically in the formal theory, this is what will happen. A couple of a positive chirality and a negative chirality spinor will combine and pick up a mass, or maybe two of them come and become zero modes. But either way, this particular combination doesn't change as things pick up a mass. So that's the index. What else I need? I need the index density. So A roof of the tangent space of your manifold times the Chern character. This is known as the index density. The reason for this name is that if there was no boundary, if this bit was not here, you could compute the index this quantity that's about the number of zero modes by doing some integral or some local density. That's why it's called the index density. And the way this is constructed, you have something first that depends on the tangent bundle. So this is something that you can construct easily to all orders. I'm just going to write the first few terms. Okay. So it seems like just introducing new definitions, but at some point I will stop. This is known as the Pontryagin class. It's a class by itself in, so Pi belongs to H4i of your manifold with integral coefficients. But there's this nice isomorphism known as the Chern-Simons isomorphism. There's a homomorphism. Isomorphism that if you tensor sorry. Okay, so I need to say one more thing. You take the formal sum of all the p's and you tensor it by the rational numbers. So I'm going to call this thing just P of my manifold and tensor Q. This has a nice expression. This is the determinant of 1 plus IR divided by 2i. And this is the curvature too. All right. So this seems a little bit abstract, but in practice, what you need to do to compute this thing, if you want to compute it from first principles, which is something that you rarely do, but if you were to, the thing you can compute is the curvature 2 form, so you know something about the tangent bundle on your manifold. You compute the curvature 2 form of this bundle, and then you take the determinant. This is a matrix. You take the determinant of this. Right? And this gives you a formal sum of things of degree 1, so degree 0, degree 4, degree 8, and so on. And those are the Pontryagin classes tensored with the rational numbers. Okay. One more thing. Then we are done. Okay, so I also wrote CH of E. This is the Chern character of E. E is the bundle to which, so this is the B bundle to which the fermion couples. So we have a B, I lost track of the primes, a B prime prime, I think, B prime prime bundle, which is the one that lives in S. The fermion in these D plus 2 dimensions is coupling to that bundle in some representation. So it could be in the fundamental, it could be in the joint, in a representation that you like. And then you construct the Chern character of this bundle in the following way. You compute the exponential of IF, which is the curvature of the bundle. Okay. So again, that's just the definition. Let's see. Yeah.
So this L genus and also the Chern character, this only capture the pathetic local anomaly.
Yeah.
The Z class type of anomaly.
That's right. These are the local. There's the local data. If you want, this is the curvature of your bundle. This is a way in which I can make this precise. If you go and read the paper of Dai and Freed, they have a very direct relation between this object and the curvature of, and the connection on this determinant line bundle.
So how about including those other maybe MAR2 class, not the Z class of the anomaly, like involving, for example, steeple Winnie class?
Oh, yeah, well, that can happen, yeah, if you have, is it okay if I come back to that later? Yeah, so this is just to answer your question, but may not be understandable to everybody else. This is one example of an anomaly theory. Of course, there are many, and some of them include the steeple Winnie classes. This is fun.
Where is the global anomaly in this formula? Is it there?
I will explain that in a second, but you will have global anomalies whenever this vanishes. Otherwise, it makes no sense to talk about global anomalies. But data invariant is still non-zero. All right, so let me do some examples. These are very abstract. And I will also put some examples for you in the exercises. Yeah, so what's my first example? Let's do the simplest thing I can think of, a U1 bundle on S4. I can try to apply this formula. So note, and this will be true for all my examples at this moment, but later on I will do examples without this assumption, that the boundary of S4 is 0. So in that case, in this case, I don't have the eta invariant contribution. So the index of the Dirac operator on S is just the integral of A of genus times the Chern character. Okay, so I need to know a little bit more.
So, sorry, I thought that S was supposed to be odd dimensional.
There was? Okay, that's good because I didn't understand the question. All right, so we want to compute this index, and I'm going to do it by integrating this right-hand side. Okay, so one thing I haven't perhaps emphasized, and perhaps I should, is that if this is a d-dimensional manifold, so in this case d equal to 4, when you do this integral, of course, you want to pick up the part of degree equal to d. So I need the parts of degree 4.
You're considering like theory in 2 dimensions.
No, in 4.
But the anomalous theory lives in 2 dimensions, right?
If this was the anomaly of something, the relevant something will be 2-dimensional. You're right. At the moment, I just want to play with the index formula to get a feeling for what this is. Yeah. Yeah. All right. So let's pick up the parts of degree 4. If I start with the A roof of TS, based on that formula, the parts that are relevant are up to P1. The Potterian classes are Pi is of degree 4i. So if P2 is already degree 8, too high. And similarly, the Chern character of the bundle, in this case a U1 bundle, and the relevant representation is the charge of the particle. I'm not indicating that in the notation, but that's the right thing to do. So this is e to the I f divided by 2 pi. So up to degree 4, this is going to be 1 plus if over 2 pi plus 1/2 minus 4 pi square f square.
Inaki, I really apologize. I might have been distracted, but you know, your t tilde was t glued on the two ends.
Yes.
So t tilde is a closed manifold.
Correct.
So in particular, the boundary of t tilde is 0.
Yeah, the d is on the other side, yeah. T tilde is the boundary of S.
Okay, so why do you consider eta of dt tilde as something non-trivial? And there you said, since the boundary was for 0, so eta is not a 0. What's the I might have been distracted.
No.
So why is here it's non-zero and there it's 0?
Correct. All I'm doing here is examples of this formula, forgetting for a second now the motivation for this formula.
That I understand, but what's the difference between S4?
So in that case, S would be S4.
S is S4.
That's right. And T tilde will be the boundary of S4, which is nothing.
Okay, sorry.
So in that case, there will be a special case of this formula with eta equal to 0.
I was very distracted.
No. I'll try to be more interesting. All right, so we have to pick up the parts of degree 4. So that's going to be minus 1 over 24 p1 times 1. Sorry, maybe I should say this more carefully. R of ts Chern of E, this is 1 plus minus 1 over 24 p1. So this one times this one, and this one times this one, minus a half 1 over 4 pi square f square. And these are higher order terms that don't matter. I'm integrating over S4, so that's what it is. Yeah. Sorry?
Why you keep the 0?
Well, in principle I have the 1, but of course when I integrate over S4 I get 0. Yeah. Yeah. The part that matters is this one. Okay. So I want to do this integral over S4. And in principle, you could do what I said before. You could construct the curvature 2 form of S4, construct the trace of R square, and try to integrate that. That's perfectly doable. It's a little exercise you can do if you like. But I think it's more illuminating to try to use general properties of the Pontryagin classes. So useful property is the following, that you take the integral over some manifold M of P1 and you divide by 3, you get the signature of M. So this is a 4 manifold.
But this is true only on a spin manifold, right? Or any manifold with any structure on a tangent bond.
Yeah, sorry. Here I'm viewing this as a manifold which is oriented, I guess. Yeah, to define the signature, I need the...
At least orientability.
I need orientability, yes, you're right. And I want to have some intersection formula, orientability. Mm-hmm. Any other questions? Right, so maybe to elaborate on the question, because it's interesting. What's the signature of a 4 manifold? This is true for any even dimensional manifold. So there's an intersection form, which is symmetric. So symmetric pairing, which goes from the middle cohomology, in this case 2-dimensional real coefficients, so this is just the intersection, so cap product plus integration. If you prefer to think in terms of the Poincare duals of homology, this will be literally intersection of the cycles, just valued in R. So whenever you have a symmetric bilinear form, as this is, it has a signature. So the signature of M4 is the signature of this symmetric bilinear form. So this is basically, you look at how cycles intersect with each other for R. You diagonalize this matrix, you have positives, plus ones and minus ones. You count those, that's the signature. There's an alternative description. If you want to think in terms of the RAM, you have a Hodge star, which is the number of self-dual minus anti-self-dual. Anyway, so this is the signature of the manifold. But already looking at this definition, you can guess what the signature of S4 is. So let's just start with H2 of S4 with coefficients in R, that's 0. And this is H2, sorry. So there's no 2 cycles in S4. And this implies the signature of S4 is 0. There's really nothing. So this implies the integral on S4 of P1 is 0. Of course, more efficient ways of doing this, but the general principle works in more complicated examples. Right. So that takes care of this contribution here. Now let's think about this one. So we have to compute the integral of f wedge f in S4. One way to think about this, if you like, is this is the U1 instanton number in S4, for bundle. That's going to be 0. U1 doesn't support instantons. A different way of saying this is that this integral, because these forms are closed, is an integral really in cohomology. And you cannot obtain anything non-trivial in H4 in cohomology by multiplying 2 things in H2 in cohomology, because H2 is 0. Okay. So we learned that the index of this operator on S4 is 0. Okay, that was quite a bit of work for proving that this is 0, but hopefully it gives a taste of the ideas in the simplest possible example. Let me do one that's a bit more non-trivial and a bit more interesting in practice.
Can I ask something before you raise that point? Usually, one thinks these gauge anomalies as a lack of gauge invariance, as we can see from the mapping theorem. But in that formulation, the proper way to understand this lack of invariance is by the ambiguity in the choice of pool manifold, right?
Yes, correct. Yes, that's completely true. That's an important point, and I will explain that in a bit more detail later. But it comes back to some question that was also asked before. The result of imposing that this phase is uniquely defined when you extend via arbitrary manifolds, so imposing that you don't depend on extension, is actually a stronger requirement than imposing that the mapping tori don't change the phase.
The left-hand side of this equation in that board is completely gauge invariant. All you have in the left-hand side is completely gauge invariant, and now, as you said, the anomaly is this fact of evaluate data invariant.
Yeah, exactly. So one thing I haven't emphasized is that the data invariant is gauge invariant. It's a statement about the spectrum, right? So yeah, this is a different way of looking at things. I'll try to motivate later why, particularly in the context of string theory, the prescription that you don't depend on extension is the more natural one. It's in any case stronger. So if you don't depend on the extension, you are going to be gauge invariant. Okay.
Sure, Inaki, just a quick question. Is this signature thing related to that R wedge R?
Yeah, definitely. So I didn't emphasize it, but if you do this expansion up to some constant in the front, P1 is trace R wedge R.
So it's a gravitational anomaly.
Yeah, exactly. Mm-hmm. Yeah.
A naive question. Did you comment about the signature of the the Euclidean versus Minkowski signature?
Yeah, thank you. Sorry, yes. Somebody.
How do you want Euclidean here?
Yeah, sorry, I haven't said that and I should have. Everything I say in my lecture is going to be Euclidean.
But then, would you like to give a comment about
what happens with Lorentzian continuations? You're asking me to comment on what happens with the Lorentzian continuation of this?
Yeah, how do we think about this? Maybe.
Yeah, I don't think I can comment anything apart from the fact that I expect the Euclidean condition to have to be satisfied, even if our theory is Lorentzian. I don't have a proof or nothing near the proof. So I can compute all these things in the Euclidean. I suppose it's conceivable, although I don't see very well how, that these are too strong and the Lorentzian theory does not have to obey these things. I cannot say more than that, yeah. I'll be surprised if that happens, but I don't know. All right. Let's do an example which is more interesting. So this is going to be a Weil fermion in the fundamental of SUN on S4. So very often I'm going to call the fundamental representation the box, as usual. Okay, so same story. Most of the formulas I wrote are still true. So A roof unus of tangent of S4 is going to be 1 minus 1 over 24 P1 plus terms that don't matter. And it's still true that the integral of S4 of P1 is 0. So the A roof doesn't contribute. But in this case, this thing is more interesting. So the Chern character here is going to be the rank of the representation. So this is just n. If I'm in SUN, then the first term will be something like, let me write it, trace of IF over 2 pi. This is going to be 0 because I'm in SUN. The generators are traceless. So I'm left with the contribution, which is minus 1/2 1 over 4 pi squared integral, sorry, trace of f squared, and that's it. Okay, this quantity here is the instanton number of the SUN bundle. As you say, instanton density, sorry. So putting these things together, I get that one result that's probably familiar, n plus minus n minus is the instanton number. This configuration.
So this is a trace over the fundamental, not over the adjoint?
Screw something up. I think there's a factor of 2n that I'm worried about with my system as you are. I think in my conventions that's fine. The instanton number is trace of the adjoint divided by 2n, right? And the relation is that the trace of the adjoint is 2n times the trace on the fundamental. So I could write, which I think is what, so I think it's actually a better way. This is 1 over 2n with 1 over 8 pi squared, trace adjoint. And that will be the same thing because of the relation. Right. So there's going to be an important relation to keep it in mind. If I put n instantons on the S4, then I do get some zero modes. Those are unavoidable. And the number of zero modes that I get are precisely given by the instanton number. There's a little bit stronger statement one can make. I'm not going to give a proof. That's quite beautiful, so I encourage you to read this paper. They show that if n inst is bigger than 0, then n minus is equal to 0. And if n inst is smaller than 0, then n plus is equal to 0.
Question. Is this only for the classical optical solution, this last comment?
What do you mean by?
Well, suppose you...
Oh, no, I think, yeah, this is... no. Yeah. So the argument here is about positivity. You have some positive defined operator. The argument is positively defined when the instanton number is positive. And... Oh, sorry. I think their proof, yes. Yeah, I think you can give a stronger proof. If you go to the paper, I think you're right. Yeah, thank you. All right. So this is an example of a gauge configuration that gives zero modes, but there's also interesting geometries that give zero modes even in the absence of a bundle, of a gauge bundle. So this is my last example of the index formula. So it's a neutral fermion, not charged under any gauge group. On K3. Okay, so what's K3? So there's some interesting space. Which is Calabi-Yau. So in particular, it's a spin, and in particular, that's orientable. And which has a non-trivial signature. Which is minus 60. Okay. We don't need anything from this manifold apart from these facts. Okay, so let's compute the index formula. In this case, start with this one, because I'm in a trivial representation, so this is the trace in the trivial representation of EIF over 2 pi. F in the trivial representation is 0. You guys don't act. So this is just 1. Good. And A roof on the tangent matter of K3, this 1 minus 1 over 24, P1. So if the signature of K3 is minus 16, this implies that 1/3 integral over K3 of P1 is minus 16. So the integral over K3 of P1 is minus 48. So these two things together imply that m plus minus m minus is the integral minus 1 over 24, the integral over K3 of P1, so that's 2. So in this case we get two zero modes, even if they're not charged underneath. Just because they couple to the tangent bundle and the tangent bundle is interesting enough, we get zero modes here. Maybe let me make a comment. This actually, in this case, this number had to be even. There's a version of Kramer's doubling in this case. So this is spinor. And a trivial representation, if you look at the representation theory here, there's an operator that maps eigenspaces to each other, which is non-trivial. So this has to be even. And this implies, if you look at this formula here, that the signature of the manifold, whenever this is spin, and I can apply the index theorem. Well, let's work it out. This is 1/3 of the integral of P1, and the integral of P1 is 24 times the index. Thank you. I was wondering where it went. So this is 8 times the index, and I just argued, at least said that this has to be even. So this is a multiple of 16. So this is a very useful theorem in the theory for manifolds. Perhaps you have seen this before. It's a Rocklins theorem. This is by far the most economical proof if you know the index theorem to be true. Okay, any questions? All right, so let's, yeah.
Sorry, the SU2 anomaly is like your second example? Or not?
The global SU2 anomaly?
Yeah.
No, I'll come to that. That's not encoded in these ones. So basically the index is going to tell you about the curvature. So let's do that one very quickly, just to show you there's no local anomaly, to show that there's actually a SU2 anomaly. Is much more complicated. We'll do that in the next lecture. But if you were to try to compute the SU2 anomaly, that's an anomaly for a 4-dimensional theory. So I want to compute the index in 6 dimensions. So the relevant term in that case is going to be trace of f cubed when I expand, and this is 0 for SU2, for group theory reasons, because it's pseudo real. Okay, so this might seem a little bit abstract, and it is, but it's necessary for global anomalies. But there's a connection to the Chern-Simons invariant. It goes as follows. Imagine that you take some manifold, MD, some connection B as before, and you make a small transformation to some manifold which is MD BG, so the same setup I'm discussing, but here I'm assuming that G is small. Well, maybe, sorry. I'm going to do something a bit more general. I'm going to choose a B prime, and I'm going to assume that B prime is a small deformation of B. Could be gauged, but it doesn't have to. Okay, and I'm going to assume, as is generically the case, that the index of the Dirac operator on M is 0. So I've picked up some background that there are no zero modes in here. Okay, let me call this manifold as before N. If I had no zero modes in here and I do a small deformation, there will be no zero modes along the middle. So the index of the Dirac operator on N is also going to be 0. All right. Now clearly, the boundary of N is B prime minus B. Sorry, showing the notation. So I can use the APS index theorem.
Sorry, I'm confused.
Yeah.
Why is the boundary and the difference of the?
Oh, sorry. That's going to be. Sorry. Yeah. Let me call this MD prime with the understanding that is entirely the same as MD. Okay, so this is the boundary, and I have no zero modes in the middle. So by the APS index theorem, I have that the eta invariant of the Dirac operator on M prime, B prime minus the eta invariant of the Dirac operator M is equal to minus, in my conventions, the integral on N of the index density. Now, the way we define the Chern-Simons invariant, we call it omega Chern-Simons. And it's given by a transgression, so meaning that you take the D of the Chern-Simons, you get the index density. Of course, this only makes sense locally in some sense. If you want to make sense of this more globally, you can use something known as differential cohomology, but I'll probably not have time to cover that, but I'm more than happy to explain after the lecture. Anyway, this is a geometric object you can construct, which is the Chern-Simons invariant, and which has a defining property that D of the Chern-Simons invariant gives you the index density. You may be familiar with this in the special case that you have. You're looking at the degree 4 terms in the index density, so this f wedge f will be living in here, and I'm forgetting now the curvature. In this case, omega Chern-Simons is something like a wedge d. Okay. All these expressions can be given meaning globally. All right, so using this expression and using Stokes, I get that eta of d m prime minus eta d of m is minus the integral on m prime omega Chern-Simons minus integral of m omega Chern-Simons. Okay, so what I have done, I have written this index density as d of something. Integral n of d on something is the same as integral on the boundary of n of the something, and this is this expression here. So that implies that generically, meaning as long as I don't hit zeros, the variation of n is the variation of the Chern-Simons. They are not the same object, but they're closely connected. Yeah.
I was saying that you can define the Chern-Simons without this extension trick.
Yeah.
Oh, there is a way.
Yeah, there's a way.
I see. Okay, I'll do that.
Did you say there's a way to include the gravitational piece with the differential cohomology definition?
You can, yes. Any other questions?
Are you going to talk about descent equations?
You want to have what?
The descent equations.
Ah, descent. Yeah. That's going to arrive at that point.
Sorry, I'm confused about something.
Hmm?
So M was even dimensional?
I may have mixed up notation. M here is probably d plus 1.
I thought that was the original.
No, in this argument what I have is the eta invariant that I'm evaluating some space, and I'm deforming the eta invariant a little bit. So this is going to be my original notation d plus 1, and this is d plus 1. Not to have to change everything, let me do this. Yeah, thank you. And I have a couple of those here. There you go. I think it's correct now.
That is true only under the assumption that there is no zero mode, right?
Yeah, that's correct. Mm-hmm. Yeah, so that's a very good question. It leads me to my next observation, and I think with this, I finished talking about this bit. So these two things are closely connected, but they are not the same. They are quite different. So omega Chern-Simons, the Chern-Simons form, is not gauge invariant. And it's only defined, and the integral only makes sense modulo 1. Okay, so this may be familiar statements. The fact that omega Chern-Simons is not gauge invariant, that's more or less clear from here. The fact that the integral is only defined modulo 1 has to do with large gauge transformations. And it's hopefully a familiar fact, did not do ask me after the lecture. On the other hand, eta is gauge invariant. But it jumps by 1 when I encounter zero modes. And to understand this, remember the original formula. Eta is 1/2 of the dimension of the kernel plus the sum over the signs. So if one of these goes from positive to negative through a zero mode, this sum jumps by 2, and the 2 is subset. That's of course no problem for me because I am exponentiating the eta invariant. My phase is e to the 2 pi I eta, so my exponential is well defined. They're not only different mathematical objects, they are in fact, so probably this condition should be written mod 1 if I want to include the zero modes. And the other thing I want to say is that, maybe in a different board, so for SU2 in 5D, meaning I'm interested in the 4-dimensional biofermion in SG2 in the fundamental, as before. The relevant object for the anomaly is trace of F cube in the fundamental, so a 6D object as usual. The curvature will be a 6D object. But if this is 0, it means that up to terms that are basically counter terms, my Chern-Simons invariant for SU2 in 5D is also going to be 0. Again, for the same reason, it's trace of A, which dA, dA, so that's going to be 0. So what that means is the data invariant is 0. In this theory, there's no curvature, there's no so the Chern-Simons invariant is 0. In this theory, there's no curvature. But on the other hand, I will show in the next lecture that in this theory, for some choices, of T tilde, my mapping torus, eta of the Dirac operator on T tilde is 1/2. So there is an eta invariant. The way this agrees with this formula, of course, is that my eta will be constant and the Chern-Simons will be 0. All right, so that's probably going to be in the next lecture. Thank you.